Well, I saw this integral, and definitely this is not an easy one. And I have my method. I think that my method is the best in terms of simplicity and shortness. So I wanted to share with you. Now, first, well, we know this formula from a to b, f of x dx is equal to, from a to b, f of a plus b minus x dx. Well, that could be easily proved if you haven't seen it. Uh, Perhaps you know this formula anyhow. So here, well, this plus this is half pi. So this means that half pi minus x for this one. Sine half pi minus x is cosine x. Cosine half pi minus x is sine. And similarly, this is log cosine and log sine and the dx, right? So this minus that, and this minus this becomes this from half pi 0 to half pi, and half pi, right? Half pi. Now let me put it in order: sine x, cosine x, log sine x, log cosine x dx. This time, this one is exactly my target integral. So when I move I over there, I get I is 1/2 of that, right? Is equal to 1/4 pi integral and sine x, cosine x, log sine x, and the log cosine x. Well, a little simpler compared with the given integral, right? Now, next step is that this is 1/4 pi from 0 to half pi. I write this one first. This log sine x, I could write this as a half log sine square x, right? This is log sine x, no difference. This one is the 1/2 log cosine square x, right? This one's this one's that. Sine x dx, cosine x dx could be written as a d sine square. This was a 2 sine x cosine x, so I multiply half. So it's equal. See, what's techniques of integrations? That's changing the integrand function at the same time that you keep maintain the equal sign. That's technique. Now, it's equal, but I change the integrand. So this one times this one times this one times one, it becomes pi over 32, right? Now, I'm ready for changes of variable, right? I bring t for sine square. I let t be sine square x. So this becomes 0 to 1 now, right? This is a log t, log This is 1 minus t squared, right? And dt. Wow, it's good. See, the, the integral has been much better now, simpler. Yeah. Now then, this one equal to pi over 32 from 0 to 1 log t. Now this I can change to series. Log 1 minus t, right? This is sine x. Sorry. T is sine squared. This is 1 minus t, huh? 1 minus t, which is 1 minus sine x squared. So this could be written as the series n negative t to the n. Well, I believe you know this log of 1 minus t is equal to this. Well, you, excuse me for not skip the detail here. That's simply changing log of 1 minus t into series. Now then what? Then I switch the operator because this series is convergent in this interval. Therefore, it becomes pi over 32. I bring negative outside. So negative, switch the operator, the integral, right? And I leave 1 over n outside the integral. This becomes a log of t times t to the n dt, right? Yeah. Okay. Then this is minus pi over 32 sigma 1 to infinity 1 over n. Now this one I write 0 to 1 log of t, and this is a d t plus 1 over n plus 1. Yeah. This is a t to the power n dt. Now, the reason I'm doing this, I'm prepared for the by parts, right? Yeah, this one is equal to negative pi over 32 sigma and 1 over n times n plus 1. Now this is ready for by parts, right? So it's a t n plus 1 times log of t from 0 to 1 uv, right? Minus v du. V is this. Du is 1 over t, right? And dt. Wow. This one is minus pi over 32 sigma n plus 1. For this, when t equals 0 is a 0. When t equals 0, well, It's kind of a limit, by using L'Hopital's rule. You'll find is equal to zero. Or simply to understand that this one goes to zero is faster than log t to go to infinity. Therefore, this one is approaching to zero. Now, I skip the L'Hopital's rule, right? You can do it by L'Hopital's rule, and this one is equal to minus integral and t to the n dt. Wow, it's good. Now then, this negative cancel out is a pi over 32, and sigma 1 to n, and 1 over n plus 1. This integral is easy, is t to n plus 1, n plus 1, 0 to 1. So it's a end up with pi over 32 sigma and n times n plus 1 square. Wow, it's good. So my I is equal to, I continue here, my I is equal to 1 over 32 sigma 1 to infinitive n times n plus 1 square. Very good. Okay, this is our integral. Now, how to continue? Okay, well, continue here by using no more integration, but rather the series. 32. This could be written as by what? By partial fractions, right? This is n a plus n plus 1 b plus n plus 1 square c. Wow. You know partial fractions, right? I skipped the determination, determining of ABC, right? A is equal to 1, B and C equal to negative 1. Sorry, okay, you can fill up finding ABC, right? So my I is equal to pi over 32 sigma this is 1, this is a negative 1, right? So this is equal to 1 over n minus 1 over n plus 1. This is first two terms. And the second term is a minus n plus 1 square. Wow, very good. Now, this is a telescoping series, right? You must know it. Telescoping series equal to 1. So this is equal to 1, right? Yeah. Minus pi over 32 sigma 1 minus n square, yeah. Well, this is series. This series is 1 minus 2, 1 over 2 square plus 1 over 3 square plus 1 over 4 square, and so on. Right? So this is almost a puzzle problem, right? The missing one. So it's a Basel problem at pi over 6. Missing 1, right? Minus 1 will be equal to this. So this is nothing but this. Just missing 1. Okay? So this is pi over 32 minus pi over 32 Basel missing 1, right? Yeah, that's it. Yeah, good. So this is becomes 32. This is a 1, becomes a 2 minus pi square over 6. Wow. I got a result, There's no sophisticated integrals. So this is a very good method, you know. There's no sophisticated method, but rather straightforward, the elementary steps, and find the same result. Thank you.